Play that music too loud. Show me what you do now. We don't have to go out. Welcome to my house. Welcome to my house. Welcome to my duck off the crib, the spot, the pad. But my house is your house if you throwing it back. Excuse me if my home trading is sad. Soon as these happy faces say you can run with the cash. Home run, slam dunk, touchdown pass. Mi casa es tu casa, so it ain't no holding back. Another shot of vodka, you know what's in my glass. It's my house, just relax. Welcome to my house, baby, take control.
Whoops.
We can't even slow down. We don't have to go. Cheers to this. Welcome to my house. Play that music too loud. Show me what you do now. We don't have to go out. Welcome to my house. Welcome to my house. Welcome to my house.
Hey, I heard you were a wild one. Ooh, if I took you home and be a woman, show me how you do. I wanna shut down the club with you. Hey, I heard you like a wild one.
Like crazy, foolish, stupid, Carly on my mouth is pumping music. I might lose it, glass to the roof, how we lose it. I don't care tonight, she don't care, we like almost there, the right vibe, ready to get high, ain't no surprise, take me so high, jump for no time, search for no crowd. Oh, then I got.
So this is good. Hello, everyone. Can everyone hear me? I'm curious, what image do you see? Do you see two photos of my dog, Dobby? Can you also see my video with the wonderful background? Awesome. Okay, obviously we'll just hang out here until 11 o'clock. I'm going to make sure other people can get on. So let me do something over here shortly. Hold on. Am I recording this? I hope I am. Hold on. Pause record. Zoom recording. Okay, there we go. That works. Awesome. Hello, Ronan. Hello, Ellie. Hello, Elena. Hello, Henry. Hello, Tom. I'm going to play some music. Can you hear the music?
It's my house, come on, turn it up. Hear a knock on the door and the night begins. Cause we've done this before, so you come on in. Make yourself at my home, tell me where you been. Pour yourself something cold, baby, cheers to us. Sometimes you gotta stay in, and you know where I live. Yeah, you know what we is. Sometimes you gotta stay in. Welcome to my house, baby, take control now. We can't even slow down. We don't have to go a while. Welcome to my house, play that music too loud. Show me what you do now. We don't have to go a while. Welcome to my house. Welcome to my house. Morning comes and you know that you wanna stay. Close the blinds, let's pretend that the time has changed.
Ah, there it is.
Keep your
Okay.
clothes on the floor, open up champagne. Let's continue tonight, come on, celebrate. That's how we do. Sometimes you gotta stay in, and you know where I live. Yeah, you know what we is. Sometimes you gotta stay in. Welcome to my house, baby, take control now. We can't even slow down. We don't have to go a while. Welcome to my house, play that music too loud. Show me what you do now. We don't have to go a while. Welcome to my house. Welcome to my house. Welcome to my duck off the crib, the spot, the bag. But my house is your house if you throwing it back. Excuse me in my home, draining the sand. Soon as these happy faces land, you can run with the cash. Home run, slam dunk, touchdown pass. Mi casa es tu casa, so it ain't no holding back. Another shot of vodka, you know what's in my glass. It's my house, just relax. Welcome to my house, baby, take control now. We can't even slow down. We don't have to go. Cheers to this. Welcome to my house. Play that music too loud. Show me what you do now. We don't have to go. Welcome to my house. Welcome to my house. Welcome to my house. It's my house.
All right, I see so far we've got Alana, we've got Brendan, we've got Corinne, Elena, Declan, Ellie, Henry, Kai, Lucy, Mitchell, Noah, Orion, Ronan, Ryan, Tom, Avery, Isabel, Susan. Welcome to all of you. Again, we're just going to wait a few more minutes to see who else. Whoa. To see who else shows up. Gus, I see you just joined. Katie, welcome. Susan, welcome as well. It's really warm where I'm at and sunny, as you can tell from the background. Again, if this is your first time, you may want to kind of play around with the controls here a little bit that you have at Zoom. There are things you can do in terms of raising your hand and giving me feedback along the way. Also, you can send private messages to each other, I believe. You can send a private message to me. I know that for a fact, and I think you can do it to each other. So you may want to do that as well. Feel free to reconnect with people as you feel like you need to. Hello, Charles. Welcome. I see Alex. I see you just came on. Elena, I see you just came on. Elena Keller. Welcome. I see Ian just got on. Excellent. Again, we're just going to wait about another 2 minutes and then we'll get going here. And just a reminder, feel free to connect with each other as well. You can chat the whole group or you can chat individually to other people, I believe. Mitchell, yeah, go ahead and send out that link. If you have useful links to offer to people, about the physics content, or really honestly anything that you think could be helpful to others at this time, please go ahead and put that in the group chat as well. If you didn't realize it, I am actually not only posting videos afterwards, but I'm also posting text of what is on the group chat. So you'll have that available to you as well. Okay. Also, you got to keep it PG. Thank you. Sorry, I had to go let out my dog. She's probably gonna bark a few times during this next time we have together. Got 30 participants. Let's go about another 45 seconds and then we'll get started here. Welcome, Coleman. Good to see you, or at least see your name. What island am I on? Why doesn't everyone come up with an island name that could be the island? And again, try and make it punny, of course. So anyway, there you go. There's your challenge to think about for the next few minutes. Hold on, I gotta let my dog in. Hey, come here. Come on. Come here. Come here, Thomas. Come here. Come here. Come here. Okay. Those of you who stayed on to the very end last time got to see actually my dog in real time. Those of you who did not, I'll try and do that again here. Okay, I think we're gonna get going here. So I'm doing this time on my laptop. Last time I did it on my desktop. So I might have a little more trouble here just because the screen is smaller. Okay, but let's begin. Again, as usual, welcome everyone, thank you for coming. And I'm actually going to stop my video because really you don't need to keep seeing me. Okay, before we get started, again, it'd be a good idea for you to have a calculator data booklet, although I'm not sure we're gonna do any calculations. Well, there is one problem, we're gonna do some calculations. And your journal and notebook. Again, I think everyone can see and hear me clearly. If not, you can kind of say something in the sort of group chat. And those of you who weren't here last class, last webinar, this is my dog, Dobby. You're going to hear her bark from time to time. And this was a picture I took of her yesterday, a couple pictures. People asked for more pictures of Dobby. And maybe she'll become the HL Physics mascot, who knows. Okay, so let's get started here. And so to get started, again, I just want to emphasize in this very difficult time, the biggest #1 priority is please take care of yourself and your family. Be a good socially responsible citizen, and everything else is secondary. Please do not worry about your IB physics grade. I'll say it again, do not worry about your IB physics grade. If you have specific concerns, send me a remind message or an email message and we can work through them, I'm sure. My goal here during this time period is to just try and help you continue learning physics in the best way that we can together. Okay. All right. So with that in mind, let's keep talking about feedback I got from you after the first webinar. The positives I generally heard was that me narrating the slides was helpful to many of you, and that it was also fun to be able to communicate with other classmates and ask questions in the chat that could be answered not only by me, but by the other classmates. And I just want to emphasize that I strongly encourage you to connect with other classmates during this time, answer each other's questions. Again, I do believe there's a way for you to send messages to each other privately without everyone seeing them. If someone can confirm that for me, that would be great. I know I can send, and you can send me messages privately. So please, this is meant to be community time as well. And please use it as that as well. I did get some suggestions for improvement. One was to go more slowly, and I'm going to try and do that today. Please, I'm just warning you, originally I thought the webinars, I'd try and keep them to around 25 minutes. The first one we did ended up being more like 33, 35 minutes, and I thought I was going about as fast as I could, and some people felt I was going too fast. So it is likely that these webinars are going to be closer to 40 to 55 minutes or maybe even an hour. But again, if you can only attend 30 minutes of it and then you have to get off, that's so be it. That's do what you can. And then again, know that I'm recording these and I will basically always be uploading these within 24 to 36 hours. Also, some of you may have noticed I posted the slides ahead of time for this webinar, and I'll try and do that in the future. I can't promise it 100%, but I'll do my best. Okay, and I just got confirmation from Mitchell that private messages do work. Awesome. Thank you, Mitchell. And I'm going to try and check the chat room more frequently for questions. Okay, so let's talk about what we're going to do as well. Whoa, okay. Also, just know there's going to be another short survey at the end of this webinar. And so things under consideration that I'm thinking about maybe adding to the webinars in the future. One is warm-up questions. As you notice, there's a fair amount of dead time there when everyone's kind of logging in for a good 5 to 8 minutes or so. So I thought maybe a warm-up question that you could try while you're waiting for everyone to get on, like the beginning of class, that might be a good thing. More polling questions. You're going to see I'm going to put up a polling question here later on. And then also something that Mr. Shulman and I were talking about is Zoom has this capacity to do breakout rooms where you can actually, I can actually assign you to 3 or 4 other students, and then you can actually, at a moment that I indicate, go into your own little virtual conference, and you could actually see and hear each other and talk. And maybe you're doing that to work on a problem set or problems that I've given you, or maybe questions I've posed to you. So those are some things I'm going to ask your feedback for in that second post-webinar survey. So please make sure you take a few minutes at the end of this webinar to do it, or sometime later. Okay, if you have other ideas, there will also be a spot in that survey for you to offer them up. So there's nothing new here to talk about other than I just want to emphasize again, these are the suggested due dates for items. If you are running late on these items, it is not a problem. I will not penalize you. Please just try to the best of your ability after you've fulfilled priority number 1 to complete these things, okay? The essential question, I actually should have updated that and I didn't. Today, we're going to be talking more about Cepheid variables. We're going to be talking about something called the cosmological Doppler effect or Doppler shift. We're going to be talking about the expansion of the universe, and we're going to be talking about dark energy a little bit. Okay, so I do want to do a little bit of a review of Hertzsprung-Russell diagrams as well before we get into the Cepheid variables. So let's jump right into it. Those are the kind of things we're just going to talk about here. The last bullet we'll touch upon briefly. Okay, first question, of course, is why do carnivores prefer moon rocks over Earth rocks? It's a valid question. Why do carnivores prefer moon rocks over Earth rocks? And the answer is because the moon rocks are meteor. Okay, so I decided because I couldn't hear you guys all laughing hysterically like you always do in class, I put that laugh track in there, so hopefully you like that. Awesome. Okay, I'd like you, to the best of your ability, just from memory, take the next 15 seconds, trying to remember what those covered up boxes are, what's underneath those covered up boxes, 1 through 6. I'll give you about 10 seconds, go. By the way, if you didn't know, this is a Hertzsprung-Russell diagram. All right, 3, 2, 1. Let's start talking through these. Remember, on the Hertzsprung-Russell diagram, I'll just reveal them all at this point. Most important is to understand that this is a graph of temperature versus luminosity, relative luminosity, we could say, and it's a log-log scale. And remember, we talked last class about the fact that this long diagonal here is the main sequence, right? And so that long diagonal is where stars could basically spend 80–90% of their lifetime. And then we talked about the giants and the supergiants. The red giants and the red supergiants are up here. We're going to talk more about these. And then down here is the white dwarfs. Okay, so again, this is a strategy for you to kind of test yourself and try and remember things that are important. Okay, let's talk a little bit more about each of these kinds of stars. We've touched upon them, but I feel like it's important to at least for you to be able to at least give a description, 2 to 3 sentence description of what these red giants and other stars are about. So remember, the red giants are those stars. That's the next stop in the sort of stellar evolution after a star has completed its time on the main sequence. And so the red giants, basically during that time frame, they're cooler, they're humongous, and they basically are there because they become humongous because they've stopped fusing hydrogen to helium, and their main involvement is now fusing helium into heavier elements, and some of those heavy elements into even fusing more heavier elements. Okay, and so this is, I've talked about this, but this kind of gives you a sense of how massive we expect, how big area-wise we expect our sun to get. So if you notice down here, this little dot in the corner is what the sun is currently, let's say that's the current size of the sun. And this big red circle here is the expectation of how big the sun will get when it becomes a red giant, again, more than 5 billion years from now into the future. And just notice that that is a diameter of 2 astronomical units. And in case you don't remember, the distance from us to the sun is 1 astronomical unit. So again, it is projected that the sun, when it becomes a red giant, will balloon to such a huge diameter across that it will engulf our planet and other planets. Okay, so we'll talk about that, about red giants. And then red supergiants are similar to red giants. They're just larger, remember, because they start out with more solar mass. Those are generally stars that start out with 8 solar masses or greater. And they are more luminous and bigger. And again, this is just meant to give you a sense. There's our sun, and there's Antares. So it just gives you a sense, kind of like that video did that I showed in class a few weeks ago, how big these are in comparison. Okay. This is something I just want to spend a little time on. This is review, but it's review in the context of identifying what sort of path our sun will take through its stellar evolution when it, on the Hertzsprung-Russell diagram. So notice the sun is right here in the Hertzsprung-Russell diagram on the main sequence, a very average star. It's got that luminosity of 1 because remember, we're referencing luminosity here on this vertical scale to our sun. And eventually when it becomes that red supergiant, excuse me, not red supergiant, red giant, it'll take a path that kind of looks like this, where you can see here, it'll meander a bit in this region. You don't need to know all the details about the meandering, but you do need to know that at some point it's going to become a double shell burning red giant, which we've already talked about, right? The fact that in the outer core, you've got hydrogen still burning a little bit, but really the main action, so to speak, is helium fusing into carbon. And then in the middle there, you have carbon, which is inert because there isn't the temperature and pressure necessary in the middle there to basically fuse carbon into anything heavier. And from there, we've talked about this, the sun will then expel those outer layers and a planetary nebula will occur. And you can see that there will be a descent from there into this sort of region of the Hertzsprung-Russell diagram where the white dwarfs lives. And that's white dwarfs live. And that's what our sun will become, a white dwarf. Okay, so let's talk about white dwarfs. Like I said, that's a red giant at the end of the stage. It throws off those massive outer layers, forming that planetary nebula. And what's left behind is this very dense star. And you have to realize at this point, fusion is done. There are no nuclear reactions taking place. And even though it's quite hot, it becomes really small. And that gives it a really small luminosity. And hence, it's much lower in the Hertzsprung-Russell diagram. I do want to make you aware that that doesn't mean that it's just kind of lame for the rest of its existence. There are cases where white dwarfs can cannibalize other nearby stars. They grow in mass. And remember, if they go above that Chandrasekhar limit of 1.4 solar masses, it is expected that they would at some point explode into supernovae. This is just an interesting fact. Certainly not anything I would ever test you on, but it's estimated the gravity near a white dwarf is about 350,000 times stronger than it is here on Earth. Pretty incredible. Okay, let's talk about Cepheid variables again. I want to go a little bit further into these because I want you to understand why Cepheid variables are pulsating. in their luminosity. So just a quick reminder, it was Henrietta Leavitt and the rest of the female computers who basically compiled these stars. They cataloged them over many, many years. And so if you see here, her big discovery again was that correlating the fact that if a Cepheid has a longer period, then it is intrinsically more luminous than those with shorter periods. Massive discovery, opened up a lot of things about understanding what we could do in astronomy and things we could measure about stars much further away. And one of the big ideas here that, again, I want to emphasize to you that's going to be important from here out is this idea of a standard candle. A standard candle, a Cepheid variable is a standard candle because as long as we measure its period, if we accurately measure its period, then we know its luminosity. Remember, luminosity is the power that the star generates at its surface. And so if we have an astronomical object of known luminosity, that is what a standard candle is. And that is huge for us because then we can use that known luminosity to measure other things about it and nearby stars. The most common thing we measure is, of course, distance. Okay, so, whoa, I did not mean to go that far ahead. Okay, sorry about that. Let's go back. So standard candle, big idea. Cepheid variables, pretty big idea as well. Okay, let's go to the next slide. And here is an IB bingo buzzword. Remember, we've talked about Joule heating. We've talked about other IB bingo buzzwords. This is another one, hydrostatic equilibrium. This is used often in astronomy and astrophysics. And apparently IB likes to see it a lot in test question answers from what I've seen in looking at mark schemes. What is hydrostatic equilibrium? Well, we already know what equilibrium is, right? If an object is in equilibrium, and we know that it's what? The net force on it is 0. And this applies to stars. Hydro refers to a fluid. And even though we normally think about fluids in everyday experience as being liquids, technically in science, a fluid is a liquid or a gas. Okay? So if a star is in hydrostatic equilibrium, it means the forces, the inward force of gravity is being balanced out by outward forces, outward pressure forces that we've talked about already. Okay, so that's important to know because you can talk about that in terms of basically an object being in hydrostatic equilibrium. For example, main sequence stars. Main sequence stars are said to be in hydrostatic equilibrium because over the time they're in the main sequence, they basically are the inward force of gravity is being balanced by the outward forces of gas pressure and radiation pressure. Okay, really quickly, I see a question from Ryan. Ryan, I can quickly go back and talk about standard candle. If you haven't looked at the previous webinar, I would recommend you look at that as well, because we talk about that. But a standard candle is an object of known luminosity. And in the case of Cepheid variables, we know that there is a direct correlation between the period of the Cepheid star and its luminosity, the period of the pulsation. And so that's why it's known as a standard candle, and it has helped astronomers basically estimate accurately the distances to much further objects than we can do by other means like stellar parallax. Okay, so let's talk a little bit more about Cepheid variables, what actually is going on with them. Okay, so if you look here at this diagram, I'm going to go through stages 1 through 6, and a helpful analogy to think about is you can think about a Cepheid variable kind of being like a mass on the end of a spring. And let's say something sets this mass into motion, so I displace it. We know what's going to happen. In the case of the sort of mass spring system, if I set it in motion, let me put this in purple, then the mass is going to oscillate up and down. So I want you to keep that in mind as I kind of explain through what's going on here. Okay, so a Cepheid variable star, why does it pulsate? Why does it change its luminosity? Well, here's what happens. The outer layers of that star, they lose that hydrostatic equilibrium we're just talking about. Meaning what? Meaning that the outward force of radiation pressure and gas pressure weakens enough so that the gravity force, the inward gravity force, wins out. So if that happens, then we get the phenomena where that outer layer becomes compressed. And if it becomes compressed, then it becomes more dense. And that means the photons that are being created by fusion still going on in the interior of the star, fewer of them get out because they get absorbed in the more dense outer layer that has become more dense because it's become more compressed. In other words, the star will then look less bright to us because more of those photons are being absorbed by molecules as opposed to exiting the star. Well, what happens? If those molecules internally absorb more of that radiation, they are going to heat up. So the temperature inside the layer increases, and that also builds up that internal gas pressure. Wait a second, gas pressure is one of those external forces. So in other words, as the temperature builds up, the external gas, the outward force of gas pressure also increases. And so therefore you see that eventually what's going to happen is the star is going to expand. You can almost think about it on this mass spring system as if the coiled spring has stretched so much that now the coiled spring force overcomes the gravity force, and the mass then changes direction and starts moving up. So then the outer layer is pushed outwards, and it's pushed outwards in a way that causes the following to happen. When it expands, what's going to happen to the molecules in that outer layer? They're going to become less dense, right? Because they're spread out some more. And if they're less dense, then they become more transparent, meaning more of those photons being created by the inner layers of the star are going to exit. They're not going to interact with molecules because there's more space between the molecules. So more of those photons are going to be able to leave, more radiation escapes, therefore the star looks brighter to us because we get more of that radiation here on Earth. And so you can imagine that that is basically that coiled spring moving up, 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 and then eventually what's going to happen is eventually that pressure force weakens such to the point that it's less than gravity, and we're back to the beginning, which basically is where we started, where the layer falls inward because gravity becomes the greater force for a while, and the cycle repeats itself. Okay. So that's what you get in terms of a Cepheid variable sort of understanding of why it pulsates. Looking at the chat, Henry asks, so why does this happen in oscillating patterns rather than the size moving in a direct and constant relationship with the internal pressure? I'm not sure I understand the question, the way you phrased it, Henry. I guess what I would say is, think about this mass spring. If somehow I displace it, get it out of equilibrium, and I don't honestly know the mechanism as to what initially gets a Cepheid variable star out of equilibrium, but once I get it at equilibrium, it's going to move back and forth for quite a long time. And if there's no resistive forces, it'll move back and forth pretty much forever, because it'll always in trying to get back to equilibrium, it always overshoots equilibrium position. And so therefore, there's always an imbalance that it's fighting, and it's kind of oscillating back and forth with that imbalance. Okay, so let's continue and talk about, revisit what we talked about earlier, because this is going to be important moving ahead. Remember that stars are creating all those photons. We talked about this several sessions ago, and this is a depiction of those photons leaving the inner layers of the star. But in the outer layers of the star, we have molecules of elements. And remember, each element has its own distinct signature of sort of absorption spectra, or we call it usually emission spectra, but in this case, it becomes the opposite in absorption spectra, because what we receive in our telescopes is all of the entire spectrum except for missing components, and those missing components correspond to the types of elements that are in those outer layers of the star. And the depth of those missing components corresponds to the abundance of those elements. So in other words, another way of thinking about it is, if you look, I already showed this, but I want to go to the next slide, okay, which will show you here. This is what I really want to show you. So this is kind of would be maybe what an astronomer, an astrophysicist gets and takes a look at. And so here you see the characteristic curve we would think about, but there are these divots, okay? And these divots, if you want to think about them that way, correspond to the absorption spectra, in this case, of hydrogen gas. And how deep these divots are give you a sense, or give astronomers a sense of how much hydrogen there is there compared to other gases. Okay. So this is a really key idea, and it helps us here because we're going to combine it here with another idea we're going to talk about in a moment. And that idea is this. Let's go. Oh, okay. Let me just show you. This is an example for our sun. You can see there, far and away, the two most abundant elements, hydrogen and helium, make up pretty much 99% of the composition of our sun. And then you can see we have trace elements of others. So, so our sun, like most stars, is largely hydrogen and helium. And the way we know this is because we've measured very carefully the size of those divots and the exact position of those divots to identify them. The position of those divots identify them as whether hydrogen, helium, carbon, and the depth of those divots gives us a sense of how abundant they are compared to other elements. Okay, so that basically says what I just said. So we're going to keep going here. So let's talk about the Doppler effect. And actually, while I leave it on the slide, because I expect some of you want to just write this down. You don't, by the way, you don't have to memorize this. It's not something I'm going to test you on, but the concept is something you should be familiar with. What do you remember about the Doppler effect? Just a little sound effect. Okay, that is the Doppler effect that you might hear like on a speedway, like the PIR. And that has to do, obviously, with the fact that when you have a source, when you have relative motion between the source of sound and the receiver of the sound, then the output frequency of the sound wave gets disturbed, gets distorted, you could say. If the sound waves are coming towards you, if there's relative motion towards between receiver and the source, then it's going to be a higher frequency, perceived frequency, than what the actual output frequency is. And the person on the left here of the screen, they're going to feel the opposite. That ambulance moving away from them, they're going to hear a lower frequency because the sound waves are being more and more spaced out. So why do we care about this? And what I want you to realize, if you haven't watched the videos yet, by the way, there were videos that ideally you would have watched before this webinar. If you didn't, that's okay, but I strongly urge you to watch all of them because they are very helpful to understand these concepts. So what applies to sound also applies to light. And so with that in mind, I want to go back to these spectral lines. Okay, so look here. Let's say this is the spectral lines of an element as measured here on Earth in some sort of lab. And I don't know what element this is. It doesn't really matter. If you want to call it carbon, for example, we could call it carbon. Okay, so notice, but this isn't actually what we get in what scientists get in their telescopes. Okay, they'll often get stuff that looks like this. Okay, and let's take a look at this because this looks a lot like up above here, but do you notice something about the location of all these lines? Hopefully you notice they have been shifted, okay? And they have been shifted in a certain direction. And so just like sound waves, the received frequency of the sound waves can get shifted. The same goes with light waves. If there is motion between the source of the light waves and the receiver of the light waves, the frequency and wavelength of those light waves will get shifted, okay? And so, in other words, what we have here is we have the idea that when an object is moving in a certain direction, the light waves will get shifted or towards one end, and this is what we call redshifted, okay? Because it's shifted towards the red end of the spectrum here. And then you could also imagine a scenario, and this does happen, where the frequency lines, the wavelengths, are shifted in the other direction, and they're shifted towards the blue end of the spectrum. And so this would be what we call blue shifted. So what does this tell us about the motion of the object that emitted them? Well, there's a great little mnemonic that can help you understand easily. So if something is red, it's called rabbit. And what it means is if something is redshifted, if the light we're receiving is redshifted, that means the object is moving away from us here on Earth. In contrast, if the light from the object is blue shifted, then that object is moving towards us. Let me pause here and kind of take a look at what's going on in the group chat while you think about that and ponder that. I mean, I'm just going to take a moment here to read through some of the posts people have done. Darwin asks, going back to the spring oscillating, if it'll eventually, an oscillating spring, yes, eventually will slow down and stop because there are these frictional forces. Will the star behave similarly and oscillate slower and slower until it stops? Really, honestly, Darwin, what's going to make a star stop is when it no longer has the conditions for fusion to happen in its core. So I would say it's a little different than, say, the frictional forces we're talking about here on the surface of the Earth, because you have this incredibly cauldron of fusion happening in the interior of the star, and that's really what's going to dictate what happens with the star. Just continue to read along. When looking at the spectrum, how do we measure depth? I understand how it works for the graph, but how do we measure depth abundance with only the spectrum? Ryan, that kind of goes back to what we were talking about earlier. I'll just draw it again here. If I have what I expect is something that looks like this, like from a star, a continuous spectrum, but then when I, whoops, hold on, that was not what I wanted to do. Let's go back here. There we go. But then if what I actually get are these little divots, right? Let's say this is these are the divots for one element, and then I get divots that look like this that correspond to a different element. Then clearly, this second element is much more abundant in that star than this first element. Okay, so hopefully that answered your question. Sorry to have the question pile up, but if the speed of light is constant regardless of observer, how are light waves subject to the Doppler effect? What we're talking about here is not the speed of light, but the wavelength, right? And so it basically can be shifted to the left or the right, and that gives you a sense of whether the object is moving away from you or towards you. Okay, so it's not that actually that we're going to talk about the speed of light, but that doesn't really enter into this, because the question of how quickly you receive the light is different than the question of at what frequency you perceive the light. Hopefully that helps to understand that. Yes, Nick, I think you're on the right track in answering Henry's question. How do we find the unshifted? If we only know, so Katie, just to answer Katie's question, Katie asks, if we only know the shifted, how do we know the unshifted? Well, the unshifted we measure here in the laboratory here on Earth, right? We have very good, very specific measurements for what hydrogen wavelengths are the emission of the absorption spectra of a hydrogen atom here on Earth, and a helium atom, and a carbon atom, et cetera, et cetera. So we know very detailed, very precisely, if there's no motion between the source and the receiver, what those wavelengths should be. So that's where we get the unshifted. Okay, and I see Henry tried to answer your question. I think that's a good answer as well, a good addition to the answer. Okay, all right, so let's keep going. Let's go to our second question here of the day. How do people on the moon cut their hair? Of course, they eclipse it. All right, thank you very much. Thank you very much. All right, here we go. Let's keep going. If you haven't watched this video, if you're watching this webinar afterwards and you haven't watched this video, I would pause it right now and watch this 3-minute video. We're going to keep going. Okay, so here you can see what I'm talking about, and this is applied to an actual situation. So the Doppler effect, originally we thought the Doppler effect only applied it to the visible light, but we know that it applies to all electromagnetic waves in all portions of the spectrum, what we can see and what we can't see. So that's really important to realize. But here is just an example of what this might look like. Notice these are the absorption lines from our sun, and then down here you have absorption lines from a supercluster of galaxies with that sort of designation. And we can get a sense, and here's where it's important to realize why this is so important. Knowing the shift If it's red shifted, we know it's moving away. If it's blue shifted, we know it towards. But also, here's the other important part. The magnitude of the shift tells us how fast it's moving away from us. Let me say that again. The magnitude of the shift tells us how fast the object is moving toward us or away from us. So in other words, if I see a little bit of a shift in one galaxy, I know it's moving just slightly away from us. If I see a big shift in another galaxy towards the red, again, towards the red in both these cases, then I know that second galaxy is moving away from us a lot faster than the first galaxy is. Okay? Elaine, I'm going to get your question in a moment here. So, astronomers use that Doppler shift to calculate precisely how fast stars and other astronomical objects are moving toward or away from the Earth. Okay, so in other words, let me say use the magnitude of the Doppler shifts. I think that's a better way of saying it. It's how big the shift is that tells us how fast these objects are moving with respect to us. And so you can see this galaxy here has been estimated to be moving at about 7% the speed of light away from us. Because how do I know that? Because it is shifted towards the red. So rabbit, red away, it's moving away from us. And we're going to do a calculation here just so you know how to work this. Okay, so, oh, nice little graphic there. Notice the blue shift when the object's moving towards us, red shift when it's moving away from us. I'm getting a message that my internet connection is unstable. So if you could raise your hand if you can still see and hear me, that'd be great. Okay, I'm seeing a bunch of people raise their hands, so it sounds like things are good. I'm gonna keep going. Thank you. You can lower your hands now. Okay, why is the Doppler shift so important? And here we're gonna get to your question, Lena. So way back when, meaning like early 1900s, we really thought that the galaxy, or the universe was static, and there was reasonable logic to offer that explanation. It seemed to look static. It didn't seem like things were getting further away from us or closer towards us in terms of what we could measure. And if that were the case, if we had the universe that had a fixed size, what might you reasonably predict about the ratio of blue to red Doppler shifts observed from galaxies? Well, if the universe is static, then you would probably have to guess that when we observed galaxies and stars, that we would see pretty much the same number of blue shifts as red shifts, right? I mean, there's no reason to think about any less. Just kind of a random assortment of stuff kind of out there. Some of it's going to be moving towards us, some of it's going to be moving away from us, and it's probably going to be about half and half, or pretty close to that. Well, a startling fact was discovered in the 1920s. Okay, and this fact was discovered by, there's your answer again. This fact was discovered by a gentleman named Edwin Hubble. He made these very meticulous observations, and I'm sure he was supported by a cast of figures, probably some of whom are women working behind the scenes. But he discovered that the absorption spectra of pretty much all distant galaxies showed a redshift. This is just mind-boggling and mind-blowing. And it was especially at the time, and I would say it still is today when you think about it. So if everything is red shifted, that means everything is moving away from the Earth. You know, that's just odd, and it just kind of led to the most likely scenario. The most likely conclusion is that if everything is moving away from each other, then at some point in the past, all of that stuff must have been much closer together. And if you work that logic backwards all the way to its sort of logical conclusion, then you have to come up with the idea that at some point in the past, all matter was concentrated in a singular point. And then some event, and that event we call the Big Bang, caused the rapid expansion of all this matter, of this singularity, to move away from each other and to actually create the universe that we're talking about here, create space itself. So the big conclusion, the Big Bang, is that in the beginning, matter was concentrated in one point, and some sort of event caused it to spread apart. And this is an incredibly foundational conclusion in cosmology, in the world of cosmology. Okay, so with that in mind, I actually want to do our poll. So Henry, I see your question. I've not heard that we're forecasted to collide with the Andromeda Galaxy. I may be ignorant about that. So I really don't know how to answer your question, that question about the Andromeda Galaxy. But here's the poll. Okay, let's launch the poll. And there's 2 questions there. I just want you to take the next 30 seconds to answer these 2 questions about stellar evolution. These are things we've studied in the past. You should have a question about our sun and stellar evolution, and you should have a question about a standard candle. Okay. I'm going to leave that out there for a little bit. I'm going to keep going, but keep answering the poll. It looks like about half of you have answered it. Some of you are still working on it. I'm going to keep going through the slides, and we'll come back to it here in a moment. All right, so let's keep going. Let me minimize that. Okay. Where is the center of the universe? Again, if you're looking at this after the fact, you'd want to pause this video. If you haven't watched this YouTube video, it's a really good one. I just want to call out one thing from the video. The absolute best analogy I have for you is this. You want to think about the universe expanding in the following way. If you and a friend are standing a certain distance apart from each other on the sidewalk, okay? The classic Doppler shift, Doppler effect we talk about is you or your friend walking away from each other or walking towards each other, and that's going to cause either a red shift or a blue shift. But that's not what we're talking about here when we talk about the universe expanding. I want to introduce a term here called the cosmological Doppler shift. The cosmological Doppler shift is this. We know that the universe, that space itself is expanding between objects in the universe that are distant from each other. So going back to the analogy of you and your friend on the sidewalk, it's not that you or your friend are moving away from each other. It's that the sidewalk between the two of you is expanding. So even if you're standing still, you are going to see a red shift of the light coming from your neighbor, coming from your friend, because the sidewalk itself is expanding. So keep that analogy in mind as we move along here, because that's important. Okay. I'm not going to talk about this slide. I want to keep moving. I want to get to this slide. All right. So this is where we get to what we call the cosmological Doppler shift. And this equation is in your data booklet. And I just want to make sure we understand what these different terms are. So I'm going to use a different color. Let's see. I'm going to use red. Okay, C we know as the speed of light. V is the speed of object. And most of the time we're going to be talking about galaxies here or individual stars. Okay, wavelength, this is the average wavelength of the received light. And this delta lambda is the difference in wavelength between what we know, between the unshifted and shifted. Okay, I didn't write that very well. Okay, so I'm cutting in and out. Raise your hand if you can hear me clearly. I see someone says that I'm cutting out, in and out. Okay, I'm seeing many participants raising their hand. So it looks like for most of you, this is still working. So, okay, good, it's better now, excellent. Okay, so going back to this, and I can see that I haven't written this out very well. You can put your hands down. So, sorry for my chicken scratch here. We're going to walk through an example here, and I think that might be the best way for you to understand this equation. So here's a recent IB question. The collision of two galaxies is being studied. the wavelength of a particular spectral line from one galaxy measured from Earth is 116.04 nanometers. The same spectral line when measured from a source on Earth is 115.00 nanometers. Determine the speed of the galaxy with respect to Earth in terms of c, the speed of light. Okay, so I need to make a correction here. This is the, down here, this lambda, this is the reference unshifted light. Okay, all right, so let's just keep that in mind. So in other words, how are we going to solve this? So let's work through this together. So we're trying to find, so we know that the difference in wavelength divided by the reference wavelength is equal to V over C. And what we're trying to solve for here is V, the speed of the galaxy with respect to C. So notice I can solve for V if I multiply both sides by C. Then I get my result that the speed of that galaxy is going to be the difference in wavelength between the shifted and unshifted light divided by the unshifted wavelength times C. So we have the information we need, because what I can do here is I can substitute in, the difference is just going to be 116.04 nanometers minus 115.00 nanometers. And that is divided by 115.00 nanometers times C. Take a moment to do that in your calculator. I'm going to do the same. So I get 1.04 divided by 115. 1.04 divided by 115 times C, and that comes out to 0.009 C. I mean, I could go 4 or 5 significant digits. I'm not going to. So our result here is that that galaxy is moving at about 1% the speed of light, based on the significance, the size of the shift that we see in the light. Okay, so let me see what's going on here with the chat room really quickly while you digest that. Okay. So Ryan asks if there's a violation of conservation of energy. There's not, Ryan, a violation of conservation of energy. It is just space that is created. But we are going to talk about something. You ask about whether energy is created. I'm going to ask you to hold off that question until I get towards the end of this lecture. Elena, you ask, why is this an approximation? I don't have a good answer for you. I believe we are approximating that we are stationary. And I believe that's part of the approximation. But I don't feel like very good about giving that answer. I'm sure there are other approximations done here, because I believe you would have to use some Einsteinian relativity to get a little more than approximation on this, I believe. Okay, so Lewis asks, what does Z stand for? And Z, let me, I really made not a great sort of, let me see here. Come on, work with me. Don't give me technical difficulties now. Of course, my computer's going to act up here. So, Lewis, your question is, what is Z? Z is the cosmological redshift ratio. So, in other words, in this case, if I asked you what is Z, Z would be 0.009. And it's just an estimate of what the redshift is in this case. The higher the redshift ratio, the faster the object is moving away from us. Okay. Okay, so already did that. Okay, the last sort of couple slides I want to talk about today. And this goes hand in hand with what Dr. Alex Filipenko talked about in his video, his 20-minute video. And if you haven't seen that video, you really need to. I would say that's an absolute must. He's funny also. I think it's a really good video, a really entertaining video. But the work that he and other teams did relates very clearly and very carefully to what's called type 1a versus type 2 supernovae. And you need to know the differences between these two. This is part of the IB curriculum, and I think it's actually really good stuff. So there are different types of supernovae, as you can see. There are more types than what I'm listing here. I'm just giving you the two that are most important from an IB perspective. And I would say IB has done a good job of identifying the two that are probably most important to understand. So in the case of the type 1a supernovae, so type 2 supernovae are kind of the ones you typically think about, which is you have this one massive star that starts out greater than 8 solar masses, and then basically at appointed point in its stellar evolution, it basically supernovas like we've talked about. But there is another way an object or star can become a supernova or go into a supernova event. And that's the type 1a, where basically you have a binary star system, a white dwarf and one other star. And what we said happens over time is that the white dwarf cannibalizes the other star and takes more of its mass over time until it gets above that Chandrasekhar limit and then becomes a supernova event. So that is a type 1a, and we're going to see why that's important. The reason why it's important is this. Scientists have determined that type 1a supernovae have a predictable peak luminosity. This is really important. Type 1a supernovae have a predictable peak luminosity, regardless of where they exist in our universe. Type 2 supernovae do not have peak luminosity that is predictable. Okay, so that's another important difference. Okay, the third difference or thing I want to talk about between type 1a and type 2 is that because type 1a have that predictable peak luminosity, they can be used as a standard candle. Remember, there's that phrase again, standard candle. Type 2 cannot be used as a standard candle. And then the final thing you need to understand between these two supernovae is this, that type 1a supernovae will not have any hydrogen lines in their absorption spectrum. And this makes sense because if I've got a white dwarf, remember that planetary nebula has already occurred, it's blown away all those outer layers, what's left is the inner layer, which really doesn't have any hydrogen in it. Whereas a type 2 supernovae will still have hydrogen lines present in the absorption spectrum because there is still hydrogen in the outer layers. So those are 4 things, and I definitely have seen IB questions where they ask you to list 2 or 3 differences. And Dr. Filipenko and his team, they used these type 1a supernovae to basically measure how, measure the expansion rate of distant galaxies and compare the expansion rate of distant galaxies looking back in the past, okay? And so the thing you need to realize is the further away a galaxy is from us, the faster it's moving away from us, remember? Because there's more space between us and it, and therefore there's gonna be more expansion, more cosmological Doppler shift for those galaxies as compared to galaxies that are closer to us. So scientists a few years ago decided to basically say, you know, one of the big cosmological questions is, what is the ultimate fate of the universe? We know there was a Big Bang, but Dr. Filipenko uses this analogy, and I think it's a good one. Let's say I'm on the surface of the Earth, and I throw this ball straight up into the air. You can imagine what's going to happen. The ball is going to move up, slow down, slow down, slow down, and then come back down to Earth. Okay? If I throw it up even harder, right, the ball is going to maybe go up higher, but eventually, after enough time, it's going to slow down and stop and maybe come back down. Now, last unit, we learned that there is a speed above which that ball will escape the gravitational pull of the Earth. And so, but remember, the whole time it's moving up, it's still slowing down. So you could imagine a scenario where it slows down, but it doesn't slow down enough to fully stop, and it just continues to move away from the Earth forever. And you can imagine that would be the maximum possible scenario where the ball basically, of course, there you go, there's Dobby. The ball basically slows until it just reaches a constant speed. And so scientists were studying these type 1a supernovae to understand what is that rate of slowing. We know that the universe is expanding. We know things further away from us are moving faster than things closer to us. But what is the slowing rate of that expansion? And to their shock, when they carefully studied this data, they discovered that the universe, in fact, is not slowing down in its expansion rate at all. In fact, it's accelerating in its expansion rate. It's as if someone threw a baseball from the surface of the Earth, and the baseball started accelerating more as it moved further and further away from the Earth. This is incredibly puzzling. It still is incredibly puzzling even to this day. And I'm going to talk about that here in a moment. But here's just an example of what you would notice if you're looking at supernovae events. And again, this is kind of like actual data that a scientist might look at. You can see here, here's your type 1a, and you know it's a type 1a because you don't see any hydrogen in the absorption spectra. Whereas the other types, you can see hydrogen here, hydrogen here, hydrogen here. Actually, that's interesting. Okay. Oh, right. Looks like 1As, 1Bs, and 1Cs don't have supernovae, don't have hydrogen in their spectra, but it's the type 2s are the ones that do. Okay. So, I talked about Alex Filipenko in Berkeley. The big idea here that I want to kind of, this is the last slide, and then I'll obviously take questions, is dark energy. Okay, so dark energy, we don't know why the universe is expanding or accelerating in its expansion. And so we've given kind of a very sort of placeholder name to it, to call it, and we call it dark energy. We call it dark energy because we really don't know what it is. We're still trying to figure that out. And basically, we know that dark energy accounts for about 3/4 of the stuff in this universe. In a few sessions, we're going to talk about dark matter, and we know that accounts for about 21% of the observable universe. And the matter that we can actually measure and interacts with us in a meaningful way so far is only about 4%. So we've reached this sort of place called the age of precision ignorance, okay? And so the reason we call it, or some scientists call it, the precision ignorance is because we can very carefully measure exactly what we don't know. It's kind of funny. So let me take a look at the chat. I'm going to leave this slide here for a little bit. Let me just take a look what's going on in the chat. And okay, hold on. So let me back up. Okay, is this particular enough to use redshift to estimate distance? We can use redshift to estimate distance, assuming we have a standard candle in that galaxy. Because remember, if we have a standard candle of sorts, either a Cepheid variable or a type 1a supernova event, then we know the luminosity of that event. And then if we know luminosity and we know brightness, then we can solve for D in that equation. I'm answering Elena's question about, is this particular enough to use the redshift to estimate distance? Alex, can you please let Dahlia out? Henry, I don't know much about the type 1b and type 1c supernovae. You're welcome to research that on your own. Alex Gubin, why is it 4% matter and 20% matter if everything we learned about particles and antiparticles suggests they all cancel each other out? Okay, so let's be clear. Dark matter is not antimatter, okay? Dark matter is something completely different from antimatter or antiparticles. And I'm going to talk more about dark matter in a future session, but I just want to make sure you realize dark matter is not the same as antimatter. Okay, and it looks like Henry answered Alex's question. Okay, so with that in mind, oh, you know what, let me go back to the poll. Hold on, end the polling, perfect. Okay, it looks like only 16 out of 29 voted. I'm not sure why. I'll share the results here. I'm really shocked that no one called a standard candle the type of candle all students need to use before they go on to a higher candle. I don't know if you get that, standard level, higher level. So just a couple things to wrap up, and then I will stay after to answer questions. Please complete that after webinar survey that you see there. I don't know if I put the link on the blog this time, honestly. I don't think I did yet. The next webinar is going to be after spring break, Tuesday, March 31st. I will put some pre-webinar activities on the blog during spring break. Thank you all for attending. Obviously, if you have no questions, feel free to get off the webinar now. I will stick around looking at the chat room for a few more questions, for a few more minutes. Thanks, everyone. Isabel asked, why don't the percentages add up to 100%? These are estimates. So they should add up to 100%. I think in some cases they might add up to 99%. Okay, if we can, Elena says, if we can calculate velocity from magnitude of redshift, when other objects farther away move from us faster, is that enough to find distance? I already answered that, I think. We can use it to find distance, Elena, if we have a standard candle of some sort for objects for an object in that galaxy. So it could be a type 1a supernova event, or it could be a Cepheid variable. Mitchell, legacy projects, I honestly don't know. I'd like to offer some sort of legacy project if for some reason we don't ever go back to the classroom before the end of this school year. I'm hoping we do, but if we don't, we'll figure out a way to do legacy projects over a distance. If you have ideas, please feel free to offer them up. Mitchell's offered the Discord link for anyone interested. Awesome, thank you, Mitchell. If you are still thinking up a question, could you let me know like in the next 30 seconds? Otherwise, I'm going to end this meeting. All right, Isabel, Dobby just went out. Hold on, let me see if I can get her back in. Hey, come on. No, I don't think it's gonna happen this time. She's too busy chasing squirrels outside. I'll try and do it next time. Okay. You're welcome, Brendan. We can surely make Dottie the official mascot if we want. I'm not opposed to that.
Here she comes.
Oh, here's Dobby. Okay, hold on a second. Dobby. Okay, you see me there? Oh, come on, Dobbers. Hey, come on. Whoa. All right. There she is. Hey, say hi to everyone. She's kind of disappearing because of the background. There you go. All right. All right. Thanks, everyone. Take care. We will talk soon. Again, please feel free to remind.com or send me an email if anything comes up, if you have questions, concerns, and remember to take that survey. Thank you. Bye-bye.